Okay, hey, it's Stereo Police back for a part two, I believe, of my impromptu video about total harmonic distortion. I've got something really cool set up here. This is going to be a lot of fun. For the few of you guys who really appreciate this stuff, this is going to be neato, really. And I'm going to explain to you what I have going on here in a minute. But before I get into this, what I hope to do, and again, I just started this series of videos yesterday, really out of nowhere, because I was tinkering around with my new THD meter, and get some papers here, and so I briefly discussed THD yesterday, and what I'd like to do over the course of the next 2 or 3 videos is to describe how one can assess THD, starting from the simplest methods all the way up to the more complicated, and starting from no test gear at all the way up through increasing amounts of I don't know what that was, increasing amounts of test gear, all the way up through the final, which will be the use of the Keithley here, which is really the ultimate for the home hobbyist, I think, on a budget, you know. But just as a recap, because this is important, and I hope my target audience for this is a hobbyist and the person who enjoys tinkering around with classic equipment, and not the engineer, not the scientist, as I mentioned yesterday. I'm not going to get into the mathematics, and I'm not going to get into all the technical mumbo jumbo and all the jargon. You know, if you type in THD and you know, read what's on the web about there, people really get it. You know, if you want that level of detail, you can get that on the web. I'm more interested in the practical aspects of measuring it and assessing it, but not to the nth degree of precision necessarily, just good enough for me to figure out whether an amplifier is functioning properly and what needs to be repaired, if anything. And of course also to assess the quality of the design and the components. But again, before, a couple of important points, and it's kind of a recap. If I'm sorry, I'm going to hold this camera. I'm sorry if it's bouncing around, but so we mentioned yesterday that, you know, in the time domain, a pure sine wave, you know, it continues to go on. Now it looks like this, and this is time, and this is amplitude or voltage, RMS, we could say, or not RMS. RMS, you don't look at it. It's we'll just call it amplitude, pure and simple. RMS is the calculation of the equivalent, what the equivalent DC would be, so to speak. It's just basically an average, a mean. Okay, so that's here nor there. Now, if we were to look at this sine wave has, of course, it has an amplitude that varies, and it has a frequency. It has a period where it starts to repeat, and 1 over that is the frequency. And in the frequency domain, okay, that's the time domain. In the frequency domain, where we plot on the x-axis frequency, and we have amplitude on the y-axis, ordinate and abscissa. What we would have, little tick marks here. Let's say this is 1 kilohertz, nice convenient number, and 0, 1, 2, 3, 4, and let's call this kilohertz, right there. If you have a pure sine wave, you're going to have a little bar right here. That represents that sine wave, and this is amplitude, just like up here. If it's a pure sine wave. if the sine wave is distorted, then harmonics have been added to it. Harmonics. Okay, let's do this. F1, F2, F3. Let's just go with F4. Okay, so the first harmonic is we're going to call the fundamental frequency. That's 1 kilohertz. The second harmonic is going to be integral numbers, integral multiplications of the fundamental. So 2K, okay, 3K, 4K, and so forth. These are the even harmonics, and F5, let's say, and these are the odd harmonics, and the fundamental frequency is considered, it's not really technically a harmonic, it's the fundamental, but it's odd. Now, one interesting thing to note, of course, once we start distorting this, then you're going to start seeing harmonics pop up, and generally the higher we go in harmonics, the lower in amplitude, you're going to be, they're going to taper off. Now, one interesting thing to note is just kind of a general rule, and there's a lot of detailed discussion about this in textbooks and on the web, is that we can ascertain a few things from the spectrum right here, from the frequency domain. One, of course, we can ascertain whether we even have harmonics, and that tells, and the degree that we have harmonics when we put in a pure sine wave, of course, tells us what the THD is. And if I'm going to call this voltage 1, voltage 2, voltage 3, voltage 4, and the calculation for THD from the spectrum is relatively simple. It's going to be the square root of the sum of the harmonics. Okay, so these are the harmonics right here. So V2 squared plus V3 squared plus V4 squared divided by the voltage of the fundamental. And from a spectrum, and I'll get into this later, we'll actually try this, we'll see how it works. From the spectrum, we can calculate with a calculator the THD. I believe this is times 100, it's going to be a percentage to get your percentage. We can do this in dB as well, but that's a whole different calculation. It's not necessary. My spectrum analyzer is capable of giving a spectrum in voltage or dB, decibel. But anyway, so that's one thing we can ascertain. The second thing we can ascertain from the spectrum, and let me redraw another spectrum here just to demonstrate this. Okay, our fundamental, almost always the highest, should be. Then we have bunch of harmonics popping up here and there, and they decrease. One thing that we can tell is given based on whether or not, let me draw another one. Not what I intended to do. I'm going to do 1, 2, 3, 4, 2, 3. Okay, let's say we notice that we only have odd harmonics. We don't have even harmonics. Well, that can tell us, and I won't get into details, that could tell us the nature of the amplifier, whether it's a single-ended, whether it's a push-pull, whether it's a push-pull with crossover distortion, that sort of thing. Won't get into that, but it's interesting to look into. And also, it's kind of musicians can probably tell relative to musical notes why this is the case, but it's generally considered that even harmonic distortion. Let me draw something with even harmonic distortion right here. 1, 2, 3, 4. Even, nothing there, a little bit 4. Okay, so even and odd harmonic distortion. Even harmonic distortion is more pleasing to the ear. And there are reasons for that musically in terms of the addition, the intermodulation and the addition of these notes and so forth, and won't get into that. But generally, even harmonic distortion is more pleasing. Odd tends to be more noticeable and not as pleasing, more distracting, let's say. And again, I think the roots of that come in music theory. which I'm not well versed in. I have read people discussing it, but it's kind of eye-watering, and honestly, I don't really give a crap. But that's sort of one thing we can ascertain from it as we look at the spectrum, and we want to figure out what's going on with the amp and how it might sound, so to speak. Another thing, the last thing I'll say is that the more that you have of the higher harmonics, beyond say 2 and 3, beyond say 2 and 3. If you got a lot of higher harmonics, it's going to sound a hell of a lot worse. Higher harmonics are way more offensive to the ear, by far, because in part these things are way far away from the original musical note. Let's say, I'm trying to put this in terms of music, but it doesn't have to be. It's way far away from the original fundamental that they're really going to become noticeable. Now I just find that interesting. It's not really going to be necessary as we progress forward here with the video and talk more about measuring. Let's get right to so just keeping all this in mind, let's look at some spectrums here. And what I want to tell you first is my setup. And what I'd hope to do is find a really shitty amplifier, which I have found right here. This is an audio amplifier, plain and simple. I took it out of this. Okay, it had a speaker built in right here. Okay, it's an old Radio Shack, and has a on-off volume knob, which is right there. Has an input and it has an output for an external speaker. Not using that because I clipped the leads from the speaker, and I'm driving. I am driving. Now this speaker is a 16 ohm, but I really want to stress this amp, so I'm driving an 8 ohm speaker. It's one of these realistics that I rebuilt. I like these things, by the way. They're pretty cool. And so I really want to stress the amp by giving it half its load impedance and requiring a lot more current than this amp really wants to give, because I really want to see distortion. Okay, but before I do that, well, okay, let's start out with this. The first that one can assess distortion without any equipment is simply, I know this is self-evident, but simply listening to music. Or if you have, you can, if you want to put in a pure sine wave, there's lots of ways to get that through apps and on your computer, or CDs with test tones and that sort of thing, and just run it through the amp and listen to it and see if it sounds like a pure sine wave, or see if there's some other offensive thing happening. It will be noticeable as you crank the amp up. Now, I chose this little low power piece of crap amp because I know it's crappy, and I don't want to kill my ears listening to a pure sine wave, as I find, if I have a 200 watt amp, of course, and I put a pure sine wave into it and crank it up to the point where it's distorting, it's going to be piercing. It might even blow a tweeter. Not sure. So that won't happen with this setup. So unfortunately, my air conditioner is running now, and it is hot as hell. By the way, it is hot. It is hot as heck in Virginia. I live in Virginia. There's my little test listening room. It is. I'm on a tangent right now, huh? I don't know if you could. I hope my lens isn't fogging. That's the backyard. This grass is dry. As you walk through this grass, it's like it kind of breaks under your feet. We've had a bit of a drought here, and it is. Yesterday it was almost 100 degrees, and I know people out west in the desert probably are laughing at that, but here that's hot. With high humidity, 110. It felt like 110 with whatever that factor is, they say, heat index. But anyway, there's my tangent. So let's first talk about, okay, let's see if we can tell the difference. And we're going to look at the signal on the oscilloscope. I have the oscilloscope across the, paralleling across the speaker, basically, so we can see what the output signal looks like. I'm going to have a 1 kilohertz test tone being put into it. I'm going to control the amplitude. with the BK zone attenuator right here. And I'm sure you can hear the test tone by now. That's what the signal looks like. You know, looks pretty pure, not bad for a crappy amp. And so let's give a listen and watch for the point of distortion. Look at that. Okay, boom, right there we have almost a pure sine wave, and listen to what happens to the sound as you see the sine wave beginning to clip. You can hear those overtones. Okay, now it's pure. Now let's keep it right at the point before it distorts, and let's look at the spectrum. Okay, and I'm going to let's see, hold on a second. Okay, so I have on here one division. Every division is 1 kilohertz. So this is our fundamental, and this is our first harmonic, our second harmonic, or third, fourth, fifth, sixth, and so forth. So let's watch the harmonics pop up as I turn up the amplitude. Okay, look what happens. We have a... Wait a minute. We have a third harmonic. Fundamental, 2, 3. So we have an odd harmonic popping up. So we had this scenario right here. Very noticeable too, you probably heard it. And another thing is of note is odd, and this is, I should have mentioned this earlier, odd harmonics happen when the waveform is distorted symmetrically. So if I've got something happening on the top and the bottom symmetrically, okay, same thing happening here as is happening down there, that produces odd harmonics. When you have an asymmetrical distortion, like in yesterday's video with that tube amp where it kind of came up, it did some soft clipping and came down like that. Asymmetrical, okay, so in other words, the distortion on the top is different from what's on the bottom. That's going to produce even harmonics. And as you could see, we have odd harmonics. Okay, there's a 1, a 2, there's 3 and 5. We have odd harmonics. Let's go back to the signal. Okay, let me go back to the FFT. And there's our harmonics. Look at that. Now when you really crank it up, oof, wow, gets really bad. Okay, so one more time. Let's see what happens when the amp really craps out, and look at the symmetrical. See, symmetrical. Top and bottom are being distorted in the same way, and that produced our odd harmonic, our odd harmonics. Okay, take it down. So you can really, I really hope that comes across with the camcorder microphone, but you could really start to hear the you could start to hear the distortion. You can hear the overtones, which is what's happening. And those, one more thing I want to show you if I can stand the noise here, is the intermodulation distortion. So what happens, without getting into dreary details, is these frequencies, as the harmonics pop up, they're modulated and they produce sums and differences, and you get sums and difference frequencies, and they become other harmonics, and the thing cascades on. So let's see if I can show you intermodulation distortion. And my ears are killing me now. Let me space this all out. Okay, now watch. Look at that. You start to see the sums and the differences on either side. It's probably going to show up better on using a resistor, but you can see on both sides of the fundamental and harmonic you get sums and differences. And look at that, they're really popping up, even down here at the evens right here. But that becomes a whole mess of intermodulation. I'm not going to get into detail about that. But just keep in mind that IM distortion is as a direct result of it tracks harmonic distortion, and IM distortion is usually higher in percentage than intermodulation distortion is usually becomes a higher percentage than THD. And if you look at, I'm probably on another tangent, but if you look at amplifier distortion curves, okay, where we have power out and we have distortion as a percentage, you'll typically see, and this varies depending on the nature of the amplifier, whether it's tubes or transistors or the nature of the topology, but you'll generally see as power goes up, you'll have some decreasing distortion. Then at some point you hit a point where the distortion just goes up almost exponentially. And I'm going to call this 1% right here, and that's usually our threshold. We have to have a threshold. We have to, when we're determining what the peak continuous power that an amplifier, or the peak power that it can output, we usually choose 1% as a threshold. You can have different thresholds, but if we're going to compare different amps, we have to choose a threshold. I like 1%. Why was I getting into this? Oh yes, so this is THD, and it usually, it starts out at very low power levels as being a little higher in percentage, and it goes down because what happens is that, and I haven't discussed noise, and noise is really a part of this equation, so to speak, but I'm just going to consider THD and pretend that there's no noise in the system, because that's a whole different ball game. But so what happens is what distortion is present at low power levels and also sometimes mixed in with the noise is a greater percentage of the signal when the power is low, because the voltage is low, right? And as the power goes up, the voltage goes higher, but that THD, the inherent THD in noise stays the same, so the relative percentages goes down to a point where the amp starts to stress. And when it starts to stress, then the THD starts rising exponentially, like that. Now, intermodulation distortion is going to follow a similar path, but it's going to be higher in level. ID or IM. It'll be slightly higher in level. Not going to discuss intermodulation distortion anymore. We're going to focus on THD. So the point so far is that there is a way to tell. There is a way to tell to test for distortion simply by listening to it. Listen to music through it. You can generally tell how how bad an amp is by listening to it, right? And if you turn on an amp and it sounds, even at low levels, it sounds like it's been cranked up and it's distorted, and it sounds like it's the rails are being hit in the power supply. You can hear it right away. You know that. So that's number one. No equipment at all. Now, the second thing I want to do is, let's say that the second thing you would, the simplest system you would need, I think, to measure THD would be, absent an expensive total harmonic distortion analyzer, as I have here, would be a spectrum analyzer that does a fast Fourier transform, like this. A spectrum analyzer. Okay, and with the spectrum analyzer, you can literally measure, as I mentioned earlier, I have a little cursor feature on here. We can measure the relative amplitudes. We can measure the amplitude of the fundamental and then the amplitudes of the harmonics, and we can run the numbers with a calculator. Okay, we can run the numbers, and maybe we'll try that. Well, it might be fun to try that and to compare it with what the THD analyzer says. To do that, I want to go ahead and hook up the crappy amp to a dummy load because I don't want to listen to tones anymore. I'm going to go ahead and do that. And something else I wanted to do, I can't remember, but yeah, let's go ahead and do that. Let's see if we can take them. Well, you know what? No. Hold on a second. While we have this hooked up, why don't we just go ahead and measure the THD using the Keithley? Just with the system we have, let's see what's going on there. I'm going to hit pause and connect the Keithley, and let's see what's happening. Okay, so there's a number of things happening. We're not using a dummy load, so we're getting the characteristics of the output of this amplifier as it is being modified by the speaker. Okay, dummy loads and speakers are two different things. But interestingly, now this little amplifier is actually pretty good in terms of THD, but I'll tell you why. It's not an old transistor amp, it's an IC amp. It's got a I don't know if you can see it down there. That's hidden by the probes there. It's got an op amp in there. It's an audio op amp. And audio op amps are pretty damn good in terms of specs. You know, they produce pretty good specifications. And this amp does pretty good. So you can see right now, okay, I've turned it up and down. Right now at a low level, we're producing a 0.2% THD. And I'm going to raise it up. Okay, you start out really low. Okay. Okay, really low, 0.3. As I raise the amplitude, 0.2. I'm going to raise the amplitude more, 0.1. There, see, it goes down as power goes up, just like that curve I just drew. But there's going to come a point when it's going to crap out. Okay, I'm going to go higher, 0.14, a little higher. Now it's 0.28, it's going up a little bit, a little higher. Now it's 0.7, now it's really starting to rise. Distortion, 12%. More distortion, 28%. Bring her back down to a pure sine wave, 1.1%. That's cool, huh? So that little op amp pretty much followed the typical distortion curve, where as power, you know, at a low level, as power goes up, distortion goes down, and it reaches a knee. And then at that knee, it goes up. Let's see where. That'll be cool. Let's see where we reach 1%. Calling that our threshold. Okay. Okay. And then I'll take a voltage measurement. Oops, that's 7. See, at 4%, we still got a weird sine wave. 3, 2, 1. 1%. Looks like a pretty good sine wave, huh? Let's see what the AC voltage is across the load. 1.6. And I don't have a calculator. 1.6. Hold on a second. Alright. So take a guess at 1% THD, how much power is being supplied to an 8 ohm speaker. Well, there it is. 0.32 watts. That was 0.32 watts, but right before distortion. So, what a kick-ass little amp, huh? But remarkably, it has low distortion below that. Anyway, I thought that was fun. Let's go ahead and hook this up to a dummy load and try to to calculate THD from a spectrum analyzer and see how that compares with the precision of and the accuracy of the Keithley, which I fully trust. I know this thing is giving me a good reading. So again, step 2, you don't have a THD analyzer. If you have a scope that has a spectrum analyzer, we should be able to calculate a reasonable THD. Should. I've never done this before. I might screw it all up, but I'm going to give it a try. It might be fun. I'm going to call this the end of part 2 and come back with part 3 because I'm running out of time today. Got to get back to work. Come back with part 3 on our manually calculating THD. I thought that was cool. Fun stuff. Yeah, we'll call it a day, and I'll come back with part 3, and we'll do the manual calculation. Thanks for watching. See you all again. Ciao.